Oh, I don't know if you want to wear. I'm not sure. This might be like. I think this is live stream too.
Should I?
Mic it up just in case. So Arun is the guy who did a postdoc with the guy from Michigan, Anish.
That's okay. We'll figure this out. Something like that. What do they do? On set, do stuff like that. Okay. Don't break it. But kind of robust, huh?
All right, let's get started. Thanks for attending the seminar this morning by Professor Max Shtein. So Max was my PhD advisor at Michigan a long time ago now. And yes, he looks younger than me, but I don't know, good genes, I guess. I was his second
student.
PhD student.
Who's in that first cohort?
So Max got his bachelor's at Berkeley, PhD at Princeton. He's been at Michigan since 2005, University of Michigan.
2004.
He's done a lot of creative research in different areas, organic electronics, and one he'll be talking about today, and origami and Kirigami. His work has been recognized by a number of awards, including a Presidential Early Career Award, College of Engineering Vulcan's Prize for Excellence in Education, Newport Award for Excellence in Leadership in Photonics and Optoelectronics, among others. And so, he was a great advisor who was always very creative in his research, and so I think he'll give a very interesting seminar this morning, so I'll just let him take it away from here. So thanks, Max.
Yeah. I'm passing some stuff around. So feel free to play with it. Try not to break it. Some of these are. We'll talk more about what these are, and some of it is just fun. That's allowed to, I think. Thank you all for being here. I appreciate your investment of time and attention to be here. That's actually, if you think about it, an hour of everybody's time multiplied by the number of people here. That's quite an investment. So I thank you very much for being here. So I should thank you as I thank my sponsors, right? Because you're kind of sponsoring this session here with all your time and attention. The other sponsors that I should acknowledge are Air Force Office of Scientific Research that funded a lot of that stuff, and some of the things that Brendan actually worked on when he started out as a graduate student in the lab was sponsored by the Air Force, and since then we've had some funding from those guys. National Science Foundation, that kicked off this origami and Kirigami-based research in our group, Department of Energy, with some of the applications that we're looking at. Things I won't really talk much about today have to do with pharmaceutical applications of another part of research in my lab, and that's sponsored by Sublime LLC, which is a startup company, and Bill and Melinda Gates Foundation for funding that. So before I get started, I want to make a couple of diversions before we get into the topic of origami and Kirigami. And the first one is I actually want us to take a deep breath. sounds kind of fruity and weird, but I took a sabbatical a few years ago, right before the pandemic, and I was trying to study a little bit of biology and medicine, and I took a class from this guy, Uri Alon, at the Weizmann Institute, who's a physicist turned systems biologist. And one of the things that he did that I now shamelessly sort of steal and apply in my lectures and talks is just to pause and take a breath every now and then, because getting more oxygen into our lungs and brains lowers the heart rate, makes us a little bit more receptive to new ideas, calms us down, cements the learning a little bit. And I actually like to do that. And I think a lot of us feel kind of maybe exhausted after the pandemic, and we're just now trying to kind of pick things up, right? And the expectation is that now that the pandemic is quote unquote over, we can all get going really hard again, but it's kind of hard. So it's okay, I think. Eventually we'll get there. So just pause and take a breath. Well, thank you for being here. So the other thing, so I want to make another quick side tour here. I want to give a shout out to an NC State person, Brian Iezzi, who was a grad student in my lab, and he got his undergrad at NC State in the materials department and textile institute here. And he had done some marvelous work on photonic structures and applications. And his recent work is actually quite exciting, and I think has a lot of legs, that has to do with textile recycling. It turns out that old clothes get thrown away and they go into the landfill, and very little of it gets reused or recycled. So about 85% of clothes, and that's a lot, right? Per person, huge amount. And one of the big challenges in trying to recycle clothes is that they're kind of blended and they're really hard to sort. And the recycling process that you would kind of use on each type of fiber has to be very different. And because our shirts and pants and things like that, and a whole bunch of other textiles, they have blended fibers in terms of their composition. Like, you don't know what to do with it. And the labels, if you think, oh, you just read the label. Well, first of all, the label lies. It turns out that the label in the majority of the time is wrong. So this is just a kind of an idea of, okay, blended fabrics. But the labels themselves lie. And that's if you're lucky to have the label on the garment to begin with. Like, if I get a garment and I think it fits and I like it and I keep it, I just tear the label off right away, right? Like, they're uncomfortable. So that stuff. And the other thing is the speed at which this has to happen. Even if the label was there, reading the label would be very, very difficult at the speed at which you need to process the stream, the waste stream or the recycling stream. So these sorters are kind of automated. Your mixed stream recycling stream that's got aluminum cans and cardboard boxes and things like that. There's ways of sorting things very quickly in an automated way. But here you actually need to know what the thing is made of and direct it accordingly. And how do you do it in an automated way? You could, in principle, use spectroscopy or spectrometry, and that's what people try to do. And one of the most common blends is cotton and polyester. But you need to know the proportion and if it's there or not. And if you look at the spectra, there are differences, but there are significant overlaps in these things. And one of the things that we figured that we could actually do is use something that doesn't necessarily overlap with these spectra and that stands out. And what we're going to use is the concept of photonic crystals here. And the idea is that some colors are pigment-based and some colors are structural-based. The idea being that if you stack, for example, materials of different refractive indices, you control interference, and so you can control the transmission and reflection properties depending on the thicknesses of the layers, the number of the layers, and the refractive index of the material comprising each layer. And you could do it in multiple dimensions. What Brian did was actually create a preform that had macroscopically stacked layers of different materials, polycarbonate, for example, and acrylate, polymethyl methacrylate, and then use a typical industrial fiber drawing process to get a geometric reduction in the transverse dimension to pull, basically from a foot size preform, you could do a kilometer of fiber. It's a very scalable process. And when you pull the fiber and you get this geometric reduction, you see that you form lots and lots of very thin layers. And what happens then, if you interrogate this stack from the outside, the reflectivity of this stack is going to be a function of the thickness of the individual layers and the materials that you include in there. And because there's a small contrast in refractive index between the two materials, you can actually engineer your reflectance peaks to be in the infrared in a region where very cheap detectors can see it. The trick here, I should just mention that there's kind of a trick to doing this stuff is we're optimizing for overtone peaks. If you kind of know optics or harmonics and things like that, we're engineering so the overtone peaks appear at the shorter end of the wavelength where cheap silicon or gallium arsenide-based detectors can be used. And you can see some photographs under different illumination. You can see photographs of these fibers included in the textile and the fabric. So anyway, the idea is that you would actually include some of these fibers in textiles at the time of manufacture. And then at the end of life, your machine that's responsible for sorting and recycling would pull a database, for example, would know what's what. The other interesting application of this is perhaps in authentication and tracing. So a lot of brands, they care about counterfeit goods. Or if you, let's say, go through the trouble of setting up a factory that uses good labor practices, environmentally friendly sourcing of raw materials, and so on, how do you know that kind of chain of responsible manufacturing is maintained all the way through? So you could start including things like that at the time of manufacture, and then it's part of the garment from the very beginning. So anyway, we think it's kind of exciting. I just want to give a shout out to NC State, who's very good in fiber technology, and Brian, who's a former student here that is in the lab doing this wonderful work. Anyhow, so to the topic at hand. So the topic for today, I want to focus on origami and kirigami applications, and specifically to energy and healthcare. And I think these two areas of research are quite important for the survival and prosperity of our civilization. And so we've increasingly focused the work in the group on energy, and then going from energy more into healthcare, and kind of almost by accident got involved in working with things like these, and started applying it to these domains. And so I want to talk to you about kind of the fun aspects of that, which you can see by playing with some of these shapes, but also some of the engineering aspects, and what we can do to apply these techniques in ways that, let's say, ordinary ways of manufacturing and configuring materials and devices could be surpassed. Okay, so that's the idea here. This is a plot, kind of a complicated, busy plot of solar cell efficiency versus year. And you could see from the very early days, the inception of solar cells based on semiconductor materials. You have steady improvements in efficiencies. Today, peak efficiencies exceed 40, maybe you could argue 50% conversion from incoming solar radiation into electrical power. The thermodynamic limit of conversion efficiency is probably around 86% if you do the calculation. Because if you think about it as, I guess, mechanical engineers, you're probably familiar with the Carnot cycle. So you can think about it as taking your working fluid with photons from the sun that emerge at 6,000 degrees Kelvin. They're coming in here. There's this wonderful magical engine called the solar cell that somehow works to create useful output. And then it rejects heat ultimately to Earth, which is at, let's say, 300 Kelvin. So you could write out the Carnot formula and you'll get efficiency of about 90%. But there's some other losses that you have to take into account, so you get back down to about 86%. So it's actually still quite a ways to go. The big question is, how do we do it cost effectively, right? So the question of cost now, all right, what's involved? You pay up front for the solar panel, and the solar panel consists of a module that has a semiconductor, the frame, the cover glass, and so on. And it has some electrical components to be able to convert the DC electricity that the solar cell natively generates into AC electricity, which a lot of our appliances use, right? Our refrigerator usually works off of AC electricity, vacuum cleaner, and so on. That's legacy, right? But it's there, and we have to be cognizant of it, so that adds a little bit to the cost. And you also have to take into account the cost of installation. That includes labor, hardware, permitting, customer discovery, customer acquisition, all kinds of other costs, right? And that together is called the balance of system. And it turns out that it's about 50-50, okay? So the cost of the module is about half of the total cost, and the rest is balance of system. So it turns out that up until fairly recently, even if somebody were to give you the module for free, it would still be very difficult to make it cost competitive with coal, let's say, or other types of electricity because of this balance of system cost being very high. And then the calculation in terms of return on investment involves figuring out how much electricity is going to be made by the panel each year, how many years do you expect that panel to work before you have to replace it, and then the contracts that you set up typically with the grid provider, the grid owner, how much are they going to pay you for this electricity that you produce during the day, right? Because somewhere the electricity has to go, right? So unless you have a huge bank of batteries that you also have to pay for, right? You have to take that into account. And then because you have to front quite a lot of money in the beginning to get all of this set up, you also pay for loans. So the 800-pound gorilla in the industry, Solar City, that operates in California, but increasingly other parts of the country, they have a lot of capital to start with, and they have a lot of capital because they operate at scale, and they can get cheap loans from a place like Goldman Sachs to do these installations. And Goldman Sachs actually likes this kind of thing because they know that sunlight is fairly reliable. Okay, like it's come up for quite a few years previously. It will hopefully continue coming up and setting at about the same time for a few more years, right? They say, gosh, it's almost as reliable as the salary of a professor at a university, right? And therefore we can give you a home loan at a very low interest rate. That's kind of the idea. So this becomes kind of a big deal, right? So predictability and reliability of these devices, it turns out to impact this, because if you have anything in your stack that, we're going to come back to this topic, because if you have anything in your technology stack, let's say, that is unreliable, you get downgraded on the loan reliability aspect, and so your cost of loan goes up. That's called bankability criterion, okay? It's something that you learn in trying to commercialize your technology. You never really learn this stuff staying in the lab and punching ahead with efficiency. It's only when you actually try to put something into practice, a new technology into practice, do you learn stuff like that. So anyway, there are two main strategies for reducing the cost of photovoltaics. You either try to reduce the cost of the solar cell, but then inevitably the efficiency drops, and then you have to go to larger and larger areas, and that jacks up the cost of installation, so some trade-offs there. Or you try to make a high efficiency cell, but that ends up being very expensive because you have to take care, you have to hire really smart people to make sure everything works really well, you have to maintain clean conditions, you have to maybe stack different layers to make more efficient solar cells, and all of that adds cost, right? And it gets so expensive sometimes that people now start thinking about, gosh, we can't make a very large cell that is super efficient because that's going to cost a lot of money. Why don't we make that super efficient cell small and just collect a lot of sunlight using cheap reflectors, concentrator PV, right? So if you look at kind of the breakdown of what, if you install a module at a particular cost, and you have a grid sort of levelized cost of electricity that you're trying to hit, depending on the efficiency of the cell, right? You have these lines where you have, okay, if I have a 10% efficient cell and my LCOE is, on the order of 6 cents per kilowatt hour, it has to be an extremely cheap module, right? But if I go to a higher efficiency cell, let's say it's a 25% efficient cell, which is the peak lab efficiency for single crystal silicon cells, for example, in practice and modules, they end up being about 20%. So you go, okay, at this price of electricity, the maximum that my cell can cost is about $50 per square meter. Otherwise, I don't break even. Does that make sense, how you do these calculations? So why? Because once you sink money into permitting and installation and everything else, you cover a certain area of the roof, have your cell sitting there for 20, 25, 30 years, okay? How much electricity are you going to be able to generate and sell back to the grid, right? Return on investment. Here's the problem that all solar cells deal with, okay? Yes, you want to make an efficient cell, but it turns out that most of the time you're throwing away 40% of the energy. Why? Because as the sun moves in the sky, I mean, I'm told that it's the Earth that rotates, but how would you know the difference, right? The movement of the sun in the sky and the change of the angle from the standpoint of the sun, the apparent area of the solar cell is shrinking throughout the day. And what you have, this blue curve over here, that's the typical amount of power you're generating at each point during the day. You have this very sharp roll-off. It's called the cosine loss because it goes as the cosine of the angle. Now, if you could rotate your solar cell, if you could tilt the panel to follow the sun, the apparent area would stay about the same, and you reclaim about 40% more of the energy when you do that. And sunflowers are really smart. They do that, right? Here's what happens in practical terms. If you look at now, this requirement for tilting the solar panel, and of course, if you have a concentrator cell, it's almost a requirement, because if you go off focus, then you lose the energy completely. You have to allow, and these panels, they usually get made in these 2-meter wide, panels, one solid panel. And so in order to tilt it, you have to have enough space to do that. The mechanism has to be pretty sturdy, and so you end up with these ground-mounted installations that need quite a bit of space. But over half the market is rooftop installations. And rooftop installations, you're trying to make it very light and very compact. And so the two things that you're trying to do, light and compact, and tilting are incompatible with each other, right? You have a design dilemma. It actually turns out that a lot of really interesting design problems and engineering problems have to do with these conflicting design requirements. You want to do one thing, you want to do another thing, and they compete with each other in this way, or not only compete, sometimes they're totally incompatible with each other. And you have to, through clever application of mechanisms or materials or physics, you have to come up with ways of resolving that kind of trade-off and having your cake and eating it too. So, like I said, it's very common. This is your typical Pareto trade-off, right? And that's what we have there. And there's a way, we think, of getting both. And how do we do that? Well, there's some invention techniques that you can apply almost kind of algorithmically once you pose the problem in the right way, is that you can use segmentation to take this and project it and make lots of tiny solar cells, right? And so what happens then is that this structure that captures sunlight and is tiltable by virtue of breaking it up into lots of different elements could potentially become rooftop mountable. And that's kind of what we did. And one of the samples that I passed around, actually, you could see that. I'll try to show it here live. This is, you see that? Okay, but when you look very closely, what happens to the individual flaps as you stretch this little Kirigami sheet, these flaps tilt. And the angle of tilt is controlled by how much you pull on it. And it's a very systematic relationship, it turns out, and you could solve it analytically. So if I want to know what the feature angle is going to be as a function of axial strain, there's an equation that describes that. And of course, as you do that, there's going to be a little bit of necking. We'll come back to this in a second here. There's going to be a necking and a reduction in the area that you have to take into account. But all of these are analytically solvable, and experimentally, it turns out that it maps. This also happens to be a mechanical metamaterial. You're familiar with this class of materials, kind of an emerging class of materials, where the Poisson's ratio, which is just the ratio of how wide it is for how wide it becomes or narrow it becomes for how much stretch you have, is a function of the geometry of the cuts, right? So if you take a piece of rubber and you squeeze it and it bulges out, it's got a Poisson's ratio, positive Poisson's ratio, it's fixed. In this case, it turns out the Poisson's ratio is a function of the cut geometry. You can see that as I make the cuts denser and longer, there's a lot less of that necking going on as I stretch it to a given length. And that's important for power generation because you want to maintain as big of an area as you possibly can as you're tracking the sun. And in fact, what happens is if we take this family of shapes, all of these shapes collapse onto the same universal curve. If I look at the feature angle as a function of axial strain, they all collapse onto the same curve. What's different between these shapes is that how far up this curve you ride depends on the width of the cuts. So the denser the cuts and the wider the cuts are relative to the width of the shape, the further up this curve you go. And that's a good thing because you lose less area that way. There's less necking that's happening. And you can track to larger and larger angles off normal, okay? So when you put all of those things together, when you put all of those parameters together, you have an optical coupling efficiency number that's a function of the angle of the sun, the light source, your axial strain, and your transverse strain, okay? So when we put all of that together and we now predict what the harvesting efficiency is going to be as a function of time of day using this kind of shape, it turns out, so this is the coupling efficiency versus source angle, right? And you increase your coupling efficiency and you get rid of this cosine loss. When you map it onto time of day, you essentially get a single panel, single axis tilt tracking efficiency using this approach. Yes, Harold.
Quickly ask, you're changing now though the area that you cover. So
yes.
The loss factor.
Yes.
Is that included in this?
We will come back to that. Yes, we will come back to that. So the assumption here, the operating assumption, as you see, right, you can see on this sheet, there's a certain amount of white space that's not occupied by your PV in the beginning. And so if I stretch this, all right, I stretch into some kind of space, right? So if I'm putting this panel on a roof, there's a little bit of empty roof area, right, that I'm not covering. So is that a good thing? Is that a bad thing? You can actually do a calculation to see when it makes a difference. So if I work with high efficiency solar panels that work at, let's say, 20+% efficiency, the silicon that's in that panel is over 80% of the cost of the module. The framing is relatively cheap. So it actually pays you to leave a little bit of room in the frame and stretch into that empty space because you're going to economize on the amount of semiconductor. As you'll see, we use about 36% less semiconductor when we do that, and it's a good break-even kind of proposition. When we look at concentrators, that's going to be an interesting concern because there's a way to solve that problem without having to have a lot of empty space, okay? But that is an issue, right? And it's cost. So you get into so-called techno-economic calculations very, very quickly with this. How do we make this? Okay, so originally when Brendan was in the group, and this is the key to like a happy academic, experience, is to have really good students. Brendan was a really good student, made some really wonderful solar cells. And at the time, we were working on organic solar cells, and the efficiencies weren't all that good. Like peak efficiencies were around 10%. Right now, you guys here make really amazing solar cells that were kind of only a dream back then. And at the time, we thought, gosh, yeah, sure, it's flexible. Let's put organic solar cells on it. And then, like, efficiency's kind of low. It's not a good break-even proposition. So not a good return on investment. Let's work with very high efficiency, very expensive cells, because that's where the economy of semiconductor makes a big difference. So I went to my colleague, who also happened to be my PhD research advisor at Princeton, who had moved a couple of years after I started at University of Michigan. He moved, Steve Forrest, he moved to Michigan to be vice president for research, so kind of oversee the whole research. But he moved to his research group too, and I knew he was doing work on gallium arsenide solar cells, high efficiency solar cells as well. And I went to him and I said, Steve, give me your best solar cells. He said, why? Said, I'm gonna cut them. Why would you do that? So I showed him all of the math, and he said, no, we're actually going to get something here. I said, okay, let's do that. So his student and my student, Aaron Lamoureux in my group, and his student or postdoc, I think at that time, Kusang Lee, worked on this together, where basically they said, okay, we're gonna make these high efficiency gallium arsenide solar cells, and we're gonna bond them to Kapton. They're actually already on a Kapton carrier, but we're gonna create an edge pattern for these cells so that we can come in with a laser and make cuts where we need to without disturbing the actual solar cell. So you can kind of see us cutting a shape in a sheet of plastic. This is Kapton, and this is just a tabletop laser that's doing the cutting, and you can see the flexible gallium arsenide solar cell here with the stack. So when we put it together, this is what it looks like when you put it all together. Kind of a small sample, but you could make them bigger. The dark areas you see here are the actual gallium arsenide, and the bright areas are the gold contacts. So when you put it together, and sure enough, it works as expected. If you don't do any stretching and you move the light source, you get these red points over here. That's your typical cosine loss, right? And then if you say, now we're going to track the sun by stretching this Kirigami, the gallium arsenide is very thin, it's very flexible at those dimensions. It just follows the curvature of the Kapton substrate, and there it goes. So you're generating more electricity than you otherwise would. Question naturally comes up, well, how reliable is it? Because we have to do it over the lifetime of the solar cell. How often do we have to do it? We have to do it twice a day, right? Once to go from east to zenith, and then from zenith, we stretch again to go to west, right? To track the sun if we were doing diurnal tracking. And you have to do that how many times a year altogether? About 700 times a year. Let's round up to 1,000, right? It's 1,000 times a year. And how long does a solar cell have to survive? Say 30 years, so you have to do 30,000 times, right? Is it going to survive 30,000 times? It turns out that the structure is actually quite robust, and you could do it thousands of times, and here we're showing only 350, but so this is like almost a year's worth, almost a year, half a year's worth. But it turns out you could do it just thousands and thousands and thousands of times, and nothing bad happens to it. So basically, sort of this promise of getting extra energy for a limited amount of semiconductor, that turns out to really work, actually, 36% extra, according to these measurements. So that enables a possibility of rooftop solar tracking, we think. And we ran out and tried to commercialize this. And at this point, I have to say we have to take a breath. Yeah, any questions so far? It is interesting, right? Like, oh, maybe there's something there. Okay, so it turns out, as we went out to try to commercialize this, we participated in this NSF I-Core process, blah, blah, blah. And we learned about bankability. And bankability, so like bankability, balance of system, and everything else, at the end of the day, you take that 36% advantage, like 36% savings, and you say, oh, now there's a little bit of extra module that I have to provide there. I'm still paying for the installation, there's balance of system, everything. At the end of the day, in terms of the levelized cost of electricity, right, you wind up with a 12% advantage over the current state of the art. 12%, like, well, and then the engineers, Black and Veatch, let's say, that go out there and they do certification of your production process to make sure that your solar cell will work for 30 years in the field. They look at it and they're like, moving parts, huh? I don't like that. Cuts? I don't like that. So the 12% win, even though if you multiply it by gigawatts and terawatts, right, it's actually a lot of money, right? It's teradollars. Trillion dollars, right? Terawatts, teradollar territory. Say that 10 times fast. It turns out to be not enough. And so you have to look for a bigger win. You have to look for much better savings than 12%. Okay, so how are we going to do that? Okay, let's look at concentration. These are typical arrangements, well, different kinds of arrangements for concentrator solar energy. On the left, you see it's a power tower concept. You have this little focal point that's on the tower up here, and an array of ground-mounted reflectors, and they focus sunlight, send it to this tower, and kind of a sophisticated tracking mechanism to be able to do that. works really well in a sunny climate like here. It doesn't work in a very cloudy place like Michigan very well. So you don't see a lot of these in Michigan, plus, snow, right? Or you have these troughs over here, and the trough could be PV, or the trough could actually be some kind of oil that you heat, and then you send that oil to a place where you use it to boil water. And you boil water, generate high-pressure steam. The steam runs a turbine, right? Same thing over here. But let's make something like that using paper. So we can actually fold up a reflector using thin reflective sheets. And if you do some optical modeling on this, you can have a little cup that focuses light into a smaller location, smaller point. And then you do something that's kind of like weird and counterintuitive, which is, I'm going to try to demonstrate it with my notebook over here, but you can probably, if you have a sheet of paper in front of you, you can do that too, is if you take a sheet of paper and you kind of bend it, like that, I guess, if you bend it, and you press on one side versus press on the other side, what happens if I press on the left or the right, this whole structure is actually going to tilt. I'll show it to you in a second, right there. So if you mount this weird looking thing on top of like a little crest, and you push on one side, on the right side, it tilts to the right. So you can put modules together like that. You can conceive of modules that are built like that, with a frame that slides around at the bottom, and you with the frame you push on one side or the other side, and you can get this whole set of kind of flower pods, if you will, to tilt in one direction or another. This is the base. This is one of the bases over here that we fabricated using laser cutting out of polyethylene terephthalate, just plastic sheet. And there's a base that slides back and forth, and you can get this little platform here to tilt. So this platform is going to become the solar cell, okay, with a little reflective concentrator. And if you look at the range of angles that you can attain by doing this, you can get plus minus 90 degrees, right? So you can tilt from horizon to horizon this way. And this is now this question about dead space in the panel. The total motion, the total displacement laterally is only about 10 centimeters in order to achieve that. For this particular geometry, you can make it smaller or larger, right? Because it's all kind of mechanical ratios here. Okay, so the dead space that you need in the panel is essentially only 10 centimeters. Regardless, right? Regardless of how big the panel is. Right? Because individually, these members are tilting, and that's only how much you need to move. This is now what happens when you put that little concentrator. This is a non-imaging concentrator, okay? So you're just collecting photons down in the bottom, okay? So with the concentrator, the aperture ratio is 10. There's like a lot of imperfections in here because it's just metallized mylar sheet. That's super, super cheap. You're getting a 6-fold optical concentration, effectively, so a 6-fold enhancement in the current. And when you put the whole module together, you also have some potential shadowing. So when you take all of that stuff, I apologize for the quality of the image here, but there's a whole array of these things. Okay, so when you put a whole module together and you take into account all of the reflection imperfections and all of the shadowing that can occur mutually between the neighboring units, between neighboring unit cells, you can still get about 4.5 times economy of a semiconductor. Okay, so remember now, if the semiconductor used to be 85% of the cost of the module, if we have a factor of 4.5 reduction in the need for the semiconductor, that starts getting to be a little bit more substantial. Okay, and the rest is just very, very inexpensive mechanism, very inexpensive materials, and so on. So that's good. Okay, what else could we do? We got kind of excited at this point. Maybe you could do even more. So if we go with something like, so silicon, you could see the bar in the inset in this plot over here. The bar on the left is a PV module cost, and at about 60 cents per peak watt cost of a silicon module, 50 cents is the silicon, single crystal silicon, the semiconductor. If oh no, sorry, the silicon's on the left here. If sorry, I beg your pardon, that was for gallium arsenide. Silicon, on the other hand, you have, at that time, this was the cost structure. About 40 cents per peak watt is everything else in the module, and about 90 cents per peak watt was the silicon. If you could use single crystal gallium arsenide made by so-called epitaxial liftoff process, working at 30% efficiency and so on, your cost targets could be a lot smaller, but it was still too expensive for terrestrial applications, right? And not very scalable. So we thought, okay, if we do the same concentration and tracking approach with gallium arsenide, we could reduce the need for gallium arsenide in that module by quite a bit, right? So, and the greater the concentration factor, the greater that reduction. So could we concentrate even further? Could we achieve much higher concentration factors to reduce the cost of gallium arsenide to nothing? To do that, we go to so-called imaging concentrators. So we look at this big reflector dish, right, with a solar cell mounted in the focal point of that, and we just miniaturize it. So that's the geometry. The solar cell is going to be over here, and that's what it looks like when you actually cut it, when you mold and cut this out of, well, plastic. So I'm going to pass around one unit cell of it, if you will. It's a molded PET sheet that has metal deposited on it, and then you come in with another sheet on top of it that carries the solar cell. So this little dark rectangle in the middle with lines coming off of it, that's an actual gallium arsenide solar cell, tiny micro solar cell that's facing downward into the concentrator. You put the two sheets together, the molded concentrator portion and then the top sheet that's carrying the gallium arsenide. You put them together, you come in with a laser cutter and you cut out the pattern, and at the same time it fuses the two sheets together. So it's a one-step process that makes the whole module. And then you pull on it. This is what the solar cell is doing. So you can see the IV curve for a gallium arsenide solar cell. I never dreamed of having an organic solar cell that could achieve a fill factor this good, and an efficiency this good, right? And these weren't even the best cells that they could produce at that time. And then when you put it in a concentrator, this curve, the blue curve over here, on this scale, it's up there, you see. And what you actually get is the red curve. And so if you look at the ratio of the currents, the short circuit current density, we're getting a factor of 80 concentration over here. Unfortunately, because those cells weren't the best cells, their fill factor wasn't great, and so the power factor took a big hit. And in terms of the power that you're getting out of this, we're only effectively a factor of 60 concentration here. And this, in part, is because the cell is getting very hot, too. So at this point, there's so much sunlight hitting that cell, right? A factor of 80 optical concentration, the cell is getting to be over 150 degrees, the efficiency starts going down, and so on. So, okay, this is kind of interesting. What else can we do? So now I passed around things with circular symmetry, okay, or rotational symmetry, if you will. If we take our, because the other thing we were interested in is dual axis tracking, because we want to do not only diurnal, but seasonal tracking, so north-south tracking as well. How could you do that? You can't do it with the linear cut pattern, so we go to these cut patterns that have rotational symmetry to them. Okay, and it turns out that there's something interesting that happens. So once you pull the shape out of plane, if you will, if you push on it and it goes cross plane, you break the symmetry. But what you could do is you could actually slide one portion of the structure relative to the other, parallel to it. And what you notice is that if I connect with an imaginary line, I connect two saddle points in that structure, that imaginary line tilts. It undergoes a tilt. And again, that tilt has a very clear, steady kind of relationship with the amount of sliding that you do, okay? And it turns out you can span a pretty wide range of angles, about plus minus 40 or 50 degrees or so. So what we're going to do now is something looks a little bit tricky, but it turns out there's a process for doing this pretty easily and cost effectively. Is we're going to drop that little concentrator that we have into this structure, okay? And then when you do the sliding, you have a tilt angle, and because this concentrator is now resting on the saddle point, the concentrator module follows that same dependence. So now we're putting this together, okay? There's your gallium arsenide solar cell in the middle of it, contacts coming out to the edges, and we're doing the tilting. And you could see, based on the measured current, as a function of tilt angle, that we're actually able to track the sun. Now, that was one unit cell of that, but we can cut arrays. It doesn't have to be one by one assembly. You can actually make arrays. And you see below here a side view of a whole array of these unit cells put together. So that actually looks promising, right? So you get a very large concentration factor when it does that. Okay, let's take another breath. Okay, so I think it's promising. We would like to do some commercialization. There's a little bit of a bottleneck right now in terms of availability of these very high efficiency cells. But at this point, what I want to do is I want to shift a little bit to discussing healthcare applications and some other fun things that you could do with origami and kirigami. Yeah? Sound good? Okay. So this, familiar with this show? Yeah. It's good, right? Let me see if I could play it.
On its way to the sun. It's going to burn up.
Oh, yeah.
Sarah?
New technology for 12.
Using hydrogels, scientists achieved their goal of creating rudimentary versions of the charged organs in these marine animals. Sarah?
What are dolphins?
Nope. Dana?
What are eels?
Eels, electric eels, yeah.
Okay, so there's the eel. So it turns out the electric eel has cells, a whole bunch of cells in its body that it can charge. And they're stacked head to tail, plus minus, plus minus, plus minus, plus minus, so that you can build up actually quite a voltage, like almost 1,000 volts. And it discharges this energy like a single very fast impulse, and it stuns its prey. And as the prey convulses, it goes in for the kill. And actually, it turns out that a huge number of marine animals, a huge number of fish, have electrosensing capabilities. So in other words, they have a way of creating a dipole and oscillating this dipole, which projects electric fields into the surrounding water. And it can see, quote unquote, what's hiding under the soil and around corners in murky waters. Okay, and eels, oftentimes, they live in murky waters, and that's what they do. So there's actually, electric, these oscillators, dipole oscillators in these animals. And they're able to polarize and depolarize these things on demand. So the eel does that, and then it can also generate this kind of huge pulse to stun prey. So to create an artificial analog of that, my colleague Mike Meyer in biomolecular engineering and his student Tom Schroeder, they created this stack of hydrogels where there's four. Two work as semi-permeable membranes with positive and negative ions, and two work as sources of ions. And so you create the stack, and ions then go through the semi-permeable hydrogels, and you get polarization across the boundaries of these hydrogels. And what happens now, you can start generating voltages this way. And so they assemble a whole bunch of them in a tube, and it's all fine, except that because of the huge thickness, right, that you develop, there's a large internal resistance. And if you want to discharge, you don't get a lot of power out of it, right? You can stack up the voltages, but it comes at the expense of current, right? There's a trade-off there. So they said, what if we try to reduce the thickness by basically creating membranes? So we figured we could do that, and then if we create a structure like this that we could somehow simultaneously squish and bring all of these hydrogels in contact at once, we get instantaneous polarization of all of the membranes at once. You create a voltage pulse, kind of like the eel. And so there's a fold pattern, actually in some of the shapes that I passed around, there's a fold pattern called the Mura-Ori fold pattern where you can distribute the structure over an area, right? And as you bring it together, it's got essentially 1 degree of freedom. As you bring it together, all of the facets come together at once. okay? So there's interesting mechanics of the structure. So we did that, and it actually turns out to work. And if you look at the internal resistance for the stack of hydrogels that are inside of a tube versus internal resistance for things that span the thickness of the membrane from which this mirror-ori pattern is made, we have a much lower resistance. So in terms of the power that you can generate, right, maximum power that you can generate, in this case, it becomes a lot higher. Here's another interesting application. This is now linear cut patterns, large sheets that are stretched over an airfoil, over a wing of an airplane. And it turns out that as you stretch it over, the protrusions of these shapes and the angle that they make into the boundary layer of the air flowing past the wing can set off microturbulence patterns in the boundary layer, and that alters the flow resistance, right? Alters the drag coefficient. And you could use it for drag steering, and sometimes you can use it for delaying stall conditions. So if you do some measurements, these measurements are done with a colleague in aerospace engineering, Dan Inman, and his student Lauren Gamble, where it shows changes in the drag coefficient depending on how much you stretch it, for example.
Can you lower it?
Huh?
Can you lower it?
There is a regime where you can actually lower it too.
I mean, the shark skin is...
Yes, yeah, it's not easy to get into that regime, but there are possibilities for doing that. And there's also this kind of whole area of fluid surface interactions for elastic surfaces that becomes quite interesting because you can engineer the elasticity of the surface through structure now, right? And so that's a whole, interesting area of research, you think. And now you can do, so, okay, let's go back to another fun thing. If you take these rotational symmetry structures and you can basically program the contours, the cut contours to adapt, to kind of drape over almost any three-dimensional envelope shape, okay? And one of the things that we realized as we were playing around with these structures is that there are points kind of around these contours that experience very large strains, and there are points that experience very little strain, or zero strain, saddle points. And if we place strain gauges on some of these locations, these strain gauges can read out how much local strain you have, and if you put them in strategic locations, it can actually kind of allow you to reconstruct almost the entire curvature, the entire shape globally. And so at that time, I crashed. I was riding my bike, crashed, busted my collarbone, and I had to do recovery, and the recovery was very painful. And I had to do all these exercises, and they had to quantify how much range of motion I had in my shoulder in order to kind of make sure that the treatment was working so they could get reimbursed, right? And the way they did it was the physical therapist would yank on my elbow and put a protractor up against the side of my body and just, okay, good, write it down. That was the sophisticated kind of tracking of progress that they had. And then I had to do exercises at home too, which I didn't, right? Like nobody does them. And so progress is slow and everything else. So like, well, could we actually, I'm not joking, this is what was actually happening right around that time when we were doing this research. I said, Aaron Efke, who was a student in the group at that time working on this, I said, can you make a sensor that like I could just use at home to make sure I'm doing these exercises or something like that? And Erin Efke was quite interested in this too because she was a student athlete. She played a lot of soccer, did a lot of track and field, weightlifting. She's like, yeah, sports medicine, cool, let's do this. And so there was kind of this...
specific locations on the substrate, you're able to capture this motion. And this can be incredibly useful for physical therapy, specific location.
Right, so what she's doing there is basically she's mounting one of these sensors, and I think I passed around some of these circular things, and there may be one with like a little strain gauge on it. Oh, no, here it is. I'll pass this around maybe. You could see there's one lame strain gauge, but we could obviously place more on the shoulder. And as you move around, she's connected to a parameter analyzer that is picking up the resistance of the strain gauges, just regular commercial off-the-shelf strain gauges, picking up the resistance number, and the resistance is indicative of the local strain. She's doing this in a motion capture studio, so there's cameras that are watching her and the markers on various points on the limbs, and that's getting the ground truth. And so now we can correlate the electrical signal that's coming off of the gauges to ground truth. And then we could do this kind of mapping where you have elevation angle, that's the sensor data is the change in the resistance, and you map it as a function of time. So you put it together, you actually start seeing distinct patterns of movement that correlate really well with the patterns of resistance change that are coming off of the sensor. And so you can go through all these different kinds of motions, and the patterns correlate actually pretty well. And in some cases, you can do things like you can rotate your limb, and it would be very difficult for a mocap system to pick up, but the sensor actually picks it up really well, the shoulder-worn sensor. So now we're in the process of working with folks in electrical engineering, Alonso Ensample and David Lips in kinesiology to try to put these wireless sensors together and deploy them in the clinic to actually measure what happens to folks. And it turns out, for example, post-surgery recovery, wow, you know, like breast cancer surgery, there's a lot of limb function that's disrupted after that, and people need to go through a PT process. And what they would like to do, the folks that are in charge of the treatment, is they would like to actually instrument people and send them back home. Because in the lab, they'll do one thing, but what happens in the home is very different. And so they'd like to be able to track people's progress and usage of the limbs at home too. So this is kind of a circuit that's sitting here in the acromion joint, part of the joint, which doesn't actually move. So the rigid circuit is not disturbed. But then you have these strain gauges. These are locations where the strain gauges are going to get dropped in. That's mounted in points where there is going to be a lot of motion. Okay. So I think that's all I'm going to try to cover today. There's lots of other things I would love to share, but that's all I want to talk about today, given this mostly mechanical engineering maybe audience, but maybe some other folks. Hopefully you can see that there's some exciting intersections. These are the folks I worked with, my group has worked with over the years. You know, there's Steve Forrest. Matt Shtein, that I should mention, is a paper artist. He and I had kind of a friendship and a collaboration that developed kind of right around when Brendan started as a student in the group. And then eventually we saw that there was this, the NSF had a call out for this kind of research. I mean, they didn't know that it was going to be this kind of research, and we didn't know it was going to be this kind of research, but we applied and we got some funding, and that's what kicked it off. Aaron Lamoureux was a student in the group that started working that. Working with PC Ku in electrical engineering, and his student Chi-Wei Chen, who was doing these little tulips, Q-Sang Lee and Steve Forrest group, and we had a collaboration with Shan Glotzer and Nick Kotov at Michigan, and John Hart, who's now moved to MIT. And currently, the students that are working on this, well, Aaron Efke just recently graduated, and Dilara Melli, who's an undergrad. We're doing kind of a show and tell at one of the homecoming games in the stadium here. And Chao Huang, who's a current grad student in the group, has done some work on that as well. Thank you very much. Yeah.
Thanks for the excellent talk. Yeah, we got a couple of minutes.
Couple minutes for questions, yeah. We have a question back there first, and then back to you, yeah?
I'm BK, I'm the solar cell engineer.
Uh-huh.
As a solar cell engineer, I have two questions for your condensed solar cell system. So it is well known that if light, the duration of solar cell is proportional to the scale of the light intensity. So I think there will be some limitations about the how
yeah.
you make this test. So if their work contains the data related to the photostability.
Yeah, so it turns out those things people have been interested in for a while, and there's a whole body of literature that looks at stability and efficiency of solar cells as a function of concentration or aging. And that kind of work can be done independently of the origami, Kirigami kind of approaches here to doing the concentration. You could just crank up the intensity or do some kind of optics in the lab to change concentration factor, for example. And so there's quite a lot of work there. In amorphous silicon cells, for example, there's quite a lot of aging that happens. If you look at very high quality, very high efficiency gallium arsenide or silicon, there's not a ton of aging that happens. And as a function of intensity, If you take care of certain recombination processes and so on, your fill factor can stay very high, right? In that case, when we took that hit from 80x to 59x, right, in terms of optical concentration and current increase to power increase, that was because the cells that we were working with at that particular time just weren't as good, right? It's like when your best student graduates that makes these really good cells with stable fill factor, new student starts learning stuff, maybe those cells aren't quite as good. So it was kind of that kind of situation. So yeah, so we haven't done a ton of that work, but the literature is out there, and you have, for example, coefficients that you can put in to predict what's going to happen as a function of temperature, as a function of age, and so on. Does that answer your question?
And one more thing is that if you concentrate light, then there will be a bunch of different combinations will happen. So,
Yep.
So that's why the graph looks like doesn't work.
That's right. Yeah. Yeah.
Then my question is that if there is many loss of efficiencies, then is there any meaning for using the gallium arsenide as well?
No, yeah, like I said, that particular cell was not the best example. Generally, these things work much better than that. There's a much lower loss in efficiency. It turns out, if you do the calculations, it's 20x concentration is probably sufficient, actually, to be economically viable. And at that concentration ratio, your temperature is much, much lower, so you don't take nearly as big of a hit. Yeah. Yeah. And we had a question here. Yeah, let's quickly get to your question.
So which part of the presentation was the Kirigami and origami?
Yeah. Which part? So origami refers to folding. Kirigami refers to cutting. Kiri, right, is cut. Ori is fold. So most of the stuff that I talked about today, the vast majority was cutting, except for that eel thing, that was mostly folding. Yeah. Does that make sense?
Any last quick question?
Yeah.
I got a quick question. So,
Yeah.
when you started about the stretching of solar cell, is because the house roof dilemma, and when you said it will actually collect 30% of the energy,
Yeah.
or
Yeah.
did you consider like actually being on a rooftop and the shadow effect of the?
Yeah, so when we did the projections and the calculations, we assumed a particular location in the US with a particular tilt of the roof with typical, annual insolation patterns. So there was, I think, in Arizona, blah, 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 right? Like stuff like that. There's a kind of a related question that's not quite shadowing, but it has to do with diffuseness of light, right? If you're in Arizona in the middle of a desert, it's very nice, collimated rays, you could say, right? But mostly parallel rays, very clear day, very little scattering. If you, on a lot of days in Michigan, for example, the light is actually very diffuse. So imaging concentrators don't work nearly as well in an environment like that. And so when we were talking to potential partners for commercialization, they were saying, well, it depends, right? If we're going into Arizona, we want the imaging concentrators. If we're going to a place like Michigan, we actually might be satisfied with just this kind of stretching thing. And there's kind of a market, and it's an interesting market, but for decorative kind of architectural applications, people want something that's kind of interesting and unusual looking. It's not a huge market, right? But people are potentially interested in those kinds of applications for even stuff like this, even though it's not the most efficient thing.
Okay, so we're out of time, so let's thank Max
Yeah.
once again.
Good. Thank you. That's great. I would like to collect those because some of them were made by Matt Shtein and some of them were made by my students, but I just want to collect those things back if possible. So pass them forward or I'll come over there. Thank you. Super, thank you.
Yeah, Matt, well, you're making big bucks. Tell these guys.
Yeah, right.
There's the man.
Yeah.
Hey.
Yo, Jan, how are you?
Nice to see you. I'm sorry I missed the first half. I was
No,
teaching
no,
class.
it's super good to see you.
Thank you for
Yeah,
visiting. Yeah, thank you. Fantastic.
Fun, right?
It's really fun. Yeah, it's been a while.
It's been a long time, yeah.
It's like you're having more and more fun. So.
Yeah, you could say fun, and that's great. But then, every time I try to write a proposal about this stuff for paper, I try to think like, okay, like what's the application? What's the story?
This is a great
Like,
story, actually. This is also.
it kind of makes for a nice story. The margins, the tough part is that solar is such a commodity scale thing.
Yes, yeah.
It's really hard. It's really hard.
But looks like we're making some really good strides.
We hope. So we'd love to talk, about other, ideas. It seems like the mechanical metamaterial thing is getting big, and soft robotics is getting kind of big. And
Yeah, I remember actually you mentioned this
All other stuff on the farm was
during the
Matt,
FA
yeah.
working with
Yeah.
him for a while, right?
Yeah, he's great. He's like just he's busy now, right? So his art really took off.
Thanks
And-
to you.
Well, I don't know. Part of it is collaboration. We ended up giving all these talks together, and so he's done really well. Now he's got a whole kind of outfitted barn with his studio.
Oh, nice.
He's got an assistant, and he's just making stuff and shipping it,
Awesome.
making it and shipping it, and it's like just really doing well. Like he's doing really, really well.
Excellent.
Yeah. Let me see. Do we have a chance to talk?
I think you're super busy. You're very popular. I think you're seeing Michael Dickey, but if you
Yes. Okay.
if you pop in, my office is right next door.
Okay.
We can chat for a few
Yeah.
minutes.
That'd be great.
Awesome.
Super nice. Thank you.
Nice to see you, of course. Yeah. Enjoy the rest of the day, and hopefully I'll see you for a few minutes this afternoon.
Super.
I think 2:30. I think you were saying Michael, I believe.
Michael Dickey, 2:30. Yep,
Yeah.
that's right.
So I'll
So
be.
you're nearby. Okay.
Yeah, I'll be
That's great.
right there.
Yeah.
Thank you.
Yeah.
See you. Hey.
Hey, man. Thank you for the wonderful talk.
Oh, sure.
So, I was at Michigan from 09 to like 13-ish with Anish.
Yeah.
For 3 to 4 years, I was there doing my postdoc, and I was just telling Brendan the same thing. Well, in the department at that point, among the grad students and the postdocs, we always used to think, Max Shtein. The thing that was going around was Max Shtein is one of the smartest guys. His ideas are completely out of the box. And today, I didn't know much about your research, I must admit, back then. And when I saw this, I could see why people would actually say something like that. This is very, very cool. Thank you very much.
Thank you for saying that. I
Thank
appreciate
you.
it.
And thanks for visiting us.
Yeah. How's your stuff? I mean, how do you like this whole faculty gig? And
Yeah, I'm enjoying it. So I've been at it for 10 years now. I'm an associate professor here now. So yeah, it's enjoying things. So I started at Colorado State, and then I moved to NC State in 2019, just before the pandemic. So
oh boy,
yeah.
That's
so,
a tough time to start a lab, right?
Yeah. But now again, when you kept saying take a deep breath, I was like feeling that's 2020. That breath is for 2020. So
yeah, I mean,
very
it's quite an interesting time, right, to try to run a research program and all of everything that's entailed, because it's not just like we're tired and the students are tired. Everybody's like no bandwidth somehow, right?
Yeah, but I don't know. You say that, but when I look at your presentation, it doesn't. It's like creativity oozing out of there. So that's really easy.
Well, thank you for saying that. I appreciate that. I always feel like, when I was in grad school, I was in electrical engineering. So like, a lot of the stuff I was doing was like plumbing. Like really just, putting stuff together. And I got into the MSc department, and I feel like at the end of the day, I come home and I work on my bike. And I was like, I should have been a mechanical engineer. And then,
Well, your talk, I don't know if
people
you
are
did
like,
it on.
oh yeah, this is like art, right?
Yeah, I
Like,
don't
how
know if
did
you
you
did it
come
on
up with that? Like, I don't know. Like, I just like,
I don't know if you did it on purpose, but it seemed well suited for mechanical engineering.
I figured that if there's gonna be a big MAE kind of contingent there, like talking about chemicals.
Airfoil, I wasn't aware of the airfoil stuff. I was like, airfoils.
I figured it'd make it a little bit more mechanical.
There was so I looked at the airfoil stuff. There was a MURI just was it earlier last year?
We applied.
Did you try? Yeah, because that's right up. You know, they were looking for meta surfaces that can reduce drag and Steve Sessio, was he doing compressible and incompressible fluids there?
There's a set of folks that do work with O&R, right? And I think.
But maybe they were doing incompressible fluids and this is more compressible fluids.
Maybe. So the Air Force just recently they had a call and we applied, so we don't know yet. You know, fingers crossed, maybe we'll get it. It was a really good team. I had a lot of fun kind of putting it together and learning, you know, from folks. We have some really good folks on the team. The O&R obviously like super. I think Anish worked a bunch with O&R.
Right.
Were you on that project at all?
So no, I was not. So there was towards the end, like the last 6 months that I was there, we got it all. We were getting things started, and then I left.
Well, you know, it's an interesting area. I have a sense that the mechanical metamaterial space is really big, right? It's grown super fast, and a lot of the folks are from this Kirigami kind of initial community.
Right.
But I don't know that they figured out what the applications ought to be.
Yeah.
Right? Like there's all this stuff about, you know, the principles and modeling and predictions and everything else, and you're like, and now what you're gonna make. And that's kind of lacking, right? So I think the machinery is there. If you could figure out what it is you're gonna make out of it, that would be good.
But aerospace stuff, at least from the MURI call, it seemed very promising. But we submitted a white paper, never got past.
The Air Force, we somehow, you know, we're lucky we got invited for the full proposal. There are 4 teams that are competing for the full proposal. I don't know that we're the favorites.
Greg Abate, right? Greg Abate?
Greg Abate is another. I think there's maybe 1 or 2 teams that are kind of the favorites, I think, for that. We're not that. But,
Never know.
Yeah, you never know. You sometimes interesting things happen like that. But it is interesting. You know, there's this whole metamaterials angle is kind of interesting because obviously, like in photonics, we've looked at a lot of stuff that Brendan's done with calculations of light interaction with these structures. I mean, it's essentially the same equations. It's the same equations that you solve, right? You just think about it in different dimensions. The dimensions are very different, right? And the way that imperfections, you know, defects and other things like that, losses come in is a little bit different. But when you write out the equations, it's the same.
Also, all the best with your MURI and
thanks.
nice to meet you. And thanks for the wonderful talk.
All right, so next you're meeting Jing.
Oh, great.
And she's going to drop me back to my office. We'll be joining us for lunch. Cool. I'll see you guys. Are you going to which one? She's on the 4th floor. Which is everything?
I think I got it.